we are going to start now one very important concept of chemical equilibrium. This is known as Chatelier's principle. Now, this tells us how an equilibrium behaves if we disturb it. For example, we will discuss the same equilibrium of PCl5 in equilibrium with PCl3 with Cl2, all gases we assume here, like this. Suppose this equilibrium is present in a certain sealed container, like this. It is present in a sealed container. This is a sealed container of a certain volume here. Now, how the equilibrium is going to behave if we change number of moles of PCl5 or number of moles of PCl3 or Cl2? Otherwise, how will it behave if we change the volume of the container? Otherwise, if we change pressure of the container, how equilibrium adjusts itself against the change that is depicted by Chatelier's principle. In theoretical form, what Chatelier's principle says that if you try to disturb the equilibrium tries to adjust itself in such a manner so that it can neglect the change of the disturbance. This is what Chatelier's principle says. Example, we have got certain moles of PCl5, PCl3 and Cl2 in a certain container at a certain temperature at equilibrium. Right now we assume the system is at equilibrium. What you do here, we put a cylinder of chlorine and certain moles of chlorine are introduced into the container. Means what we did, you increase the concentration of chlorine into the container. What will equilibrium try according to Chatelier's principle? It will try to negate this change. And for doing this means what you have done, you have increased the concentration. So, equilibrium will try to decrease the concentration of Cl2. And in such an attempt, what happens that the equilibrium starts shifting in backward direction. You can see if equilibrium goes in backward direction, then number of moles of chlorines will decrease. This is how equilibrium tries to adjust itself against the change. In a similar manner, if you would have increased the moles of PCl5 into this container, what will equilibrium try? Equilibrium try to decrease the moles. And in such an attempt, this equilibrium will start shifting in forward direction. If equilibrium goes in forward direction, moles of PCl5 will decrease in the container. Similarly, if you decrease the moles of PCl3, means product, equilibrium will try to increase the moles of PCl3, and in such an attempt, equilibrium will shift in forward direction. In simple words, if we want to tell, if you increase moles of reactants, equilibrium goes in forward direction. If you decrease moles of reactants, equilibrium shifts in backward direction. If you increase moles of products, equilibrium goes backward. If you decrease moles, equilibrium goes forward. Right? This is how the things happen here. This is effect of change. This is effect of change in concentration. If we go for volume, suppose this is taken in a piston system. Like this. We have got a piston system here. Now, what we do here is that we decrease the volume of the container. If volume of container is decreased, equilibrium tries to shift itself in that direction where number of gaseous moles decrease. If you increase the volume, equilibrium shifts in that direction where number of gaseous moles increase. Obviously, this change we have to check with respect to the pressure of the container. If you are changing the volume by increase in pressure, you are increasing the pressure, you are pushing the piston downwards, volume will decrease, pressure will increase, and equilibrium will shift in that direction where number of moles of decreasing, gaseous moles. Solid moles and liquid moles we don't have to consider here. for checking this shifting. This is purely theoretical. There is a mathematical aspect of equilibrium constant. We are going to come for this one now, how the equilibrium changes. See, we write equilibrium constant for this, Kc, and Kc for this will be equal to concentration of PCl3 into concentration of Cl2 upon concentration of PCl5. Right? Concentration is nothing but number of moles by volume. We put same thing here. This is equal to number of moles of PCl3 by volume into number of moles of Cl2 by volume upon number of moles of PCl5 by volume of the container. Obviously, V is going to be same. Why? Because all the substances are present in the same container. These are the number of moles. If we simplify this, it becomes equal to number of moles of PCl3 into number of moles of Cl2 upon number of moles of PCl5 into this V gets cancelled and we get it in denominator, so 1 by V. Now see, whatever we understood up to now theoretically, same thing we can do mathematically here. If you increase number of moles of PCl3, theoretically we said that because number of moles of PCl3 are increasing, that's why equilibrium will shift in backward direction. Understand one more term here before we proceed, and that term is known as QC. This term is known as a reaction quotient. Very important term. This is known as reaction quotient, denoted by QC. The same expression which we write for equilibrium, exactly same, this one or this one or this one, whichever you want, the same expression, exactly same, but at any instant is known as QC. The same expression only at equilibrium, if you substitute the values at equilibrium, then the same expression is known as Kc or Kp, but at any instant starting from end up to the equilibrium establishment, the same expression with same values is known as QC, reaction quotient. Now see what happens. At equilibrium, this ratio must be equal to Kc. This ratio must be equal to Kc. Right? Now, you increased moles of PCl3. As soon as moles of PCl3 you increased, the value of numerator increased. Value of denominator remained same. As a result, the equilibrium got disturbed. The value of this ratio will not be equal to Kc. Now, this will be called as QC, reaction quotient. In this case, QC, right now, QC will be greater than Kc at present. To bring this ratio back to Kc, what should happen? Denominator should increase while numerator should decrease. If numerator has to decrease, the number of moles of PCl3 and Cl2 should decrease while number of moles of PCl5 should increase. For doing so, that's quite obvious, equilibrium will have to shift in backward direction. Got it? So equilibrium starts shifting in backward direction, number of moles of PCl3 and Cl2 decrease while number of moles of PCl5 increase. Again, after some time, equilibrium comes to its original state and QC now becomes equal to Kc. So if for a certain reaction, whatever may be the case, if QC is greater than Kc, equilibrium shifts in backward direction. Right? Consider second case. You increased moles of PCl5, and theoretically we said if we increase moles of PCl5, equilibrium is going to shift in forward direction. Come back here, we check it mathematically what happened and what is going to happen. If you increase number of moles of PCl5, denominator increases, numerator constant. This ratio becomes lesser than Kc. which will be known as QC. Means in this case, QC becomes lesser than Kc. Now, if the system has to come back to equilibrium, this ratio must become equal to what? Kc. And to make it equal to Kc, what should happen? Numerator should increase, denominator should decrease. If numerator has to increase, the number of moles of PCl3 and Cl2 should increase while PCl5 should decrease. And when will this happen? If equilibrium shifts in forward direction. Got it? This is how we can say for a certain expression, if at a certain instant QC comes out to be lesser than Kc, at that particular instant reaction would have been moving net in forward direction. Remember, we are using the word net reaction would have been moving in forward direction. Backward also would have been taking place there. Right? Now, at equilibrium, when equilibrium again is established, that time we will have QC equal to Kc. There is nothing at that moment. Reaction is balanced. Both the reactions are equal to each other. One is moving in forward direction, one is moving in backward direction, will equal rates. Right? So, QC becomes exactly equal to Kc at that particular moment. Now, effect of volume also we can check very simply from here, from this mathematical expression. See, mathematically what we say, that if you increase pressure or decrease volume, in that case equilibrium shifts in that direction where gaseous moles are decreasing if you increase pressure. Again we can check for this particular moment, for this particular expression, if you see, number of gaseous moles is more on the product side. On reactant side we have got only 1 mole. On product side we have got 2 gaseous moles. 1 reactant mole of gas is giving 2 product moles of gas here. So, number of gaseous moles is increasing here. Right? Now, see how it happens. If you increased pressure, equilibrium is supposed to go back in backward direction where number of gaseous moles is lesser. Check it here. We increased volume. If we increased volume, denominator increased. If denominator increased, to bring this ratio back to equilibrium constant means Kc, what should happen? Denominator should decrease while numerator should increase. Able to understand? If denominator has to decrease, you increased volume, we increased, you push it upwards. Okay, piston is being pulled upwards. So, volume increases here. If you increase volume, theoretically equilibrium will shift in that direction where number of gaseous moles are increasing, means forward direction. Okay, here volume increased, denominator increased. To bring it back to the same ratio, constant ratio equal to Kc, now denominator should decrease, numerator should increase. When will this happen? When number of moles of PCl3 and Cl2 increase while that of PCl5 decrease. Obviously, for doing this, equilibrium will have to move in forward direction. So, effect of change in pressure, moles or concentration, whatever, we can simply check from here. Got it? This is a mathematical expression. With lesser confusion, you get the correct answer here. Right? Now, see how problems can be created here. Suppose one problem is given to you, and the problem they tell you that in a certain container, 1 liter container, we have got 5 moles of PCl5, 5 moles of PCl3, 5 moles of Cl2. Now, they ask you that now 2 moles of chlorine were introduced into the container at same temperature were not disturbing at all, we should not actually, otherwise total things change. So, he says 5 moles we have got of each one in a 1 liter container. Now, 2 moles of chlorine were introduced. Tell final number of moles of each one at final equilibrium. This is the question. There are 2 ways of solving this. The very first thing which you have to do is find the equilibrium constant for the expression. That will be Kc, we are writing here, it is not given, so we will find it. This will be equal to concentration of PCl3 into Cl2 upon concentration of PCl5. Okay. Each one has been given 5 moles. So we put it as 5 by 1 into 5 upon 5. Right? So equilibrium constant comes out to be equal to 5 in this case here. Now, what he is saying that 2 moles of chlorine are introduced into the container. Find final number of moles of each species in the container. Means once again equilibrium is established, we have to find moles. See how it will be done. You have 5 moles of each in the beginning. Now 2 moles of chlorine were introduced. So total moles of chlorine would have become 5 plus 2, 7. Right? Now, as soon as these 2 moles are introduced by using Lee-Chatelier principle, equilibrium starts shifting in backward direction. We assume at equilibrium, x moles have shifted in backward direction. So we do 5 plus 2 minus x. X moles of chlorine reacted to go backward. One thing you can understand easily, if 1 mole of chlorine reacts, this has to react with 1 mole of PCl3 and 1 mole of PCl5 will be obtained. Same way here, x moles reacted will react with x moles of PCl3 and will produce x moles of PCl5. This is going to be final number of moles at equilibrium. We substitute the values in equilibrium constant, which will give us, this will become equal to moles of PCl3, which is 5 minus x, volume is 1 only, so we should not bother much about that, into moles of chlorine, which is 7 minus x, upon this is moles of PCl5, which is 5 plus x. Right? So as you can see from here, easily the value of x can be calculated. Substitute the values here, we get what will be final moles of each one of them at equilibrium.